deviation was lower. It was 22. And it was the same number of students. I think 20 students took the test. And so, you know, that to me is like, okay, that's better. Normally what I see in a class is about a standard deviation of about 14 points. So anything over like 18 is high. So to have a standard deviation of 27 is really high. Now we do have two scores here that really affected that standard deviation. I didn't run the numbers if I take those two out, but those two had a huge impact on not only the standard deviation, but also the average. So I'm not sure how to take all of this at this point. You know, historically, exam one it's usually a little better than this, but it's also, you know, this is a new type of thing for us, right? For you taking a test the way you took it, and also just seeing my first test, like what type of tests I give, you know, that's always kind of like, okay, now you kind of know a little bit what to expect. But I'm hoping that we don't maintain this same trend. I'm hoping exam two goes better, because we only had, what, 7 students pass and 9 students didn't. So I'd like to have, you know, more than half the class pass the test. But, you know, I'm giving the same type of tests I've given in the past. I'm not changing, you know, the difficulty level or anything like that. In fact, if we go back and look at exam one, just briefly here, you know, the first 2 problems were just derivatives using chain rule and product rule, things like that. You just had to know the derivatives of these special new inverse trig functions. And, you know, so that part was, you know, I expected that you could do okay on that. Everything else I took pretty much from the book. There's always something like it in the book. So like number 2, if you look back on page 252 of the textbook, number 29 and 30 were just like this problem. If you look at 252, number 6 is like this, and then also I did one like this in class. And then the next section, I just kind of like, this isn't important that we write this down, but I'm just trying to give you an idea of like where I grabbed these. This is a problem like something in the book. This is like something in the book. These 2 are like something in class. These are out of the book. So, you know, if you go back and you actually compare your exam problems to problems from the homework, I think you'll see like they were there. You know, it was just a matter of during the test, were you able to recognize, you know, what to do? And I think I've warned you about that with this class. It's all about problem recognition and how much time you're going to invest in just trying to figure out what to do, right? So most students, once they got like the correct path, they did okay. It's just when you couldn't find that path, you just kind of get stuck, right? So any feedback from you all as far as the test or changes or anything maybe we can do differently? Crickets, huh?
I don't really have any feedback, but the part that got me was once you had the U substitution was realizing that you could then you know, change it back again to like x plus 2 equals u now, or whatever it was going to be. Like that was the part I completely forgot till like barely towards the end.
Yeah, yeah.
That's really all I've got.
So, you know, I was talking to my other class, and because they're kind of in the similar boat here, you know, not a whole lot of them passed. I had 9 of them pass and 11 of them not pass. So, you know, what I told them is, I think what would be valuable to you all is to try and take advantage of this, I guess, the technology we have, and maybe set up some of your own Zoom study sessions where you get together as a group, throw problems at one another, you know, help each other explain things to your classmates, or just, you know, take advantage of my office hours a little more. And I know that my office hours don't always fit into your life, but I'm happy to, you know, I'm here a lot, so I can meet you even if it's off my office hours. If you just text me, you know, send me a text, say, hey, I'm having some trouble, or, you know, hey, I wonder if you can throw a few problems at me on Zoom. I'll come to my computer if I'm available. And, you know, I had a few students do that, and I'm okay with throwing some problems at you, just kind of give you that like just on the spot here, let's see how you do with this. I just don't want to do that like the day before the exam or the day of the exam. I want to be doing that consistently as we progress through. So study groups, I know my other class, they did something in Canvas where they set up a study group, and we're going to see how that goes. We also have other options. I mean, we can go completely like change up things like dramatically. I mean, I already have all of the lectures for this entire course on YouTube. Like you could watch, you know, pretty much everything that I do in class with you. You can watch that. We can do it. We can like flip the classroom where you watch all the videos on your own. And then when we come here, all I do is answer questions and do problems. You know, that's something to think about. I'm not saying that let's do it. I mean, we would have to take a vote, and we would have to have like a very strong majority of you want to do that. But, you know, I just want you to know that I'm open to adapting the way that we're doing this. You know, if you have any suggestions, I encourage you to just send me an email or a text and just, you know, tell me what you would like. And we'll see if we can't, you know, make whatever adjustments need to be made so that the next exam goes better for the class as a whole. Anything else about the exam, or?
Do we have time to go over one of the problems or no?
You know, so what I plan on doing, because I had a student, I'm not sure, was it you, Alex, that asked about, someone emailed me and wanted to see if they could do corrections. No?
Definitely not, no.
It might have been my other class. So I already emailed my other class the solutions to the exam. So I can go over a problem, that's no problem. But I can also just send you the solutions. So which problem were you referring to?
Number 8.
Number 8. Yeah, so number 8 was the problem where you had x cubed in the numerator. So you had to realize that x cubed is x times x squared. And then you make a substitution of 1 plus x squared. So this is a tricky problem, but it is also, let me go back here. Number 8. See right here? So that problem right there, if I go to 6.1 in the book, no, no, not 6.1. This is a basic U substitution. So this is 5.5. Am I right here? Yeah, so this is number 34. Okay, so the thing is, like, yes, I would expect a student to maybe not right off the bat in the test remember that x cubed has to become an x times x squared, but I'm going with the assumption that you've done the homework and that that's not something new to you, like you've seen it. Now maybe you don't remember it, but it's not like I threw that at you and you never had an opportunity to ever see a problem like that. In fact, I gave you the problem. So make sure that you're doing your homework. You know, I want to be fair in these exams, and I think anytime I give you a homework problem as a test problem, I think that is somewhat a gift. You know, it's like I'm not asking you to do anything outside of your homework. As long as you've done your homework and you know it, then you're going to do relatively okay on the test. I don't mean that in a negative way, Alex. I'm not picking on you or anything like that. I want everyone to understand that I'm not pulling these problems out of the air trying to confuse you. But this is a difficult problem if you're not ready for that first step, which is the x times the x squared part. So once you make that substitution, you know, you let u be the 1 plus x squared down here. Then the derivative of it is 2x dx, which you have an x dx, so you're off by 2. And then the x squared you still have to take care of, but all you do there is just take this equation and solve it for x squared. And then everything replaces. Once you get everything replaced, You've got that, and then you can split it into two separate integrals because you have a single denominator and two terms in the numerator. And then once you get it split up, you just go power rule on that. So would you all like me to just send you the solutions? I mean, I'm not going to take test corrections. I mean, you should do them, okay, for your own benefit. But I'll just send them to you, all right? I'll email them to you.
Yes, please.
And I'll do that. I'll do that at the end of class today. Were there any others that you wanted me to discuss?
Real quick, when you have it u over 1 over the square root of u, how do you go from there to the next part over where it's u?
This right here?
Yeah.
I split it into two. So I do u over the square root of u minus 1 over the square root of u. So split it into two, right?
Yeah.
And then this right here is the same as u to the 1 over u to the half.
Yeah.
And then I subtract the exponents, right? 1 take away half, that's just u to the half. And that's this part right there. And then the other one, I just rewrite it 1 over u to the half. And then I bring it up as a negative exponent. And that gives me.
Oh, okay. Cool.
Yeah. I will also say on number, which one was it? Oh, number 3. Oh my goodness. Some of the things I saw in number 3, people were trying to do like integration by parts, basic U substitutions. And I remember I warned you all about this problem because, you know, the whole point of this problem is you have a single term in the denominator, you split it up into multiple pieces, right? And then this is just power rule. So all I'm testing here is power rule. That's it. I just want to make sure you can use power rule. But if you go start doing integration by parts on that, like it's over. Like at that point it's over because it would be impossible to do it with integration by parts. So if you're ever there taking a test and you find yourself doing stuff that you've never done, right? You're like, oh my God, like I can't believe he gave us a problem like this. Then there's probably something wrong with the approach because I'm never going to give you something that we haven't seen or done, whether it be in here in class or in your homework. It's never going to be something like that. So that should be like a little light bulb that goes off where you're like, okay, I just need to kind of like maybe move on to the next problem and come back because I'm way off on this one, you know? All right, well, the train keeps moving and we are not done yet with integration by parts. We still have a little bit of discussion well, not discussion. There's 2 more problems in the section integration by parts that 2 more problems that I want to do. And, you know, as we move forward here, I don't want you to be like too discouraged if you didn't do well on this first exam. Don't be too discouraged. But at the same time, you have to make changes. Like something has to change in the way that you're approaching it. And it's perfectly, I've seen it happen where students don't do well in the first exam, then they come back and they something just clicks and they get it going. So, you know, if after the next exam you're in the same spot, then I think you have to start considering, you know, whether or not you're going to have to retake the class. So, you know, no matter what happens, I encourage all of you to finish the class. Even if you drop it, even if you wind up having to drop the class, I recommend that you stay for the whole thing. You keep coming to Zoom sessions, you keep taking the exams. I'll grade them for you, even if you're not enrolled. I don't care, because the more you see, the better off you're going to be. That way, if you do retake the class, you will have seen the entire course and you will have a second view at it instead of just dropping and leaving, if that makes sense. All right, let's do these 2 problems. So let's start off with this first one. Now, let me warn you, these 2 problems are the last 2 problems of this section on integration by parts. So they're not obvious, they're not easy. The first one here, e to the square root of x, what we're going to do to solve this one is going to be somewhat unnatural, okay? And the reason we're going to do it is because it's going to work. But before we do that, I want to just see if we're just running through what we know already about integration, just integration in general. what are some things that we could do here to try and attack this? Does anyone have any suggestions? You know, think about what we know so far. You have to do something, right?
EU be, or EU square root of x be the u, or the
You want,
root of x
so
be
like integration by parts? Is that what you're saying?
Yeah.
Okay, so if you go integration by parts, you really only have one choice for u. Does everyone agree with that? The only u we would have is the e to the square root of x. And then the dx here would have to be, the dv would have to be the 1 dx. Okay, everyone agree? Like this is an approach we could take? Okay, so now let's differentiate. So when we differentiate this, derivative e to anything is itself, but then the chain rule is going to make a 1 over 2 root x appear, and then we'll have the dx just by the chain rule. So that would be our derivative, right? And then when we go up on the other side of the table, we take the antiderivative of 1, we're just going to get x. Okay, all right, let's see where this leads us. So from here, we know ultraviolet minus voodoo, so we're going to multiply the e to the root x times x, so we're going to have x e to the root x minus a little bit of a space there. Okay, so I'm doing voodoo now. This times all of this. And I see that I have a 2 in the denominator. I'm going to pull that out as a half. Can I say one more thing about the test? I just want to say one more thing. It's very difficult as the instructor for this course, and this is something I've dealt with, you know, every single semester I teach Cal 2, every single semester. I have students that during class, they follow, they can answer the questions, they pick the right way to go, and they do well. And then the exam comes and it's like, I don't even know who that person is anymore, you know? So I realized that for a lot of you, the testing anxiety, that part of it is real. And you're just gonna have to find a way to come to terms with that. Like somehow find a way to be better. And it's not because I need you to, it's just, this is the way academia works. I mean, you go through, and I mean, I know for me, my junior, senior level courses were often just 2 exams, midterm, final, 50%, 50. And it was crazy that I'd be there for 16 weeks, right? Be in a class for 16 weeks. But it was a test that I took that was an hour and 20 minutes long that dictated half my grade. And that's a lot of pressure, right? But that's just the way it is. I mean, it goes back to that, you know, problem I shared with my brother, the interview for the job, you know, it's like right there on the spot, you gotta be ready and perform, you know? So that's just the way it is, the nature of the beast. I mean, if I could just give you all A's just for being here and let's just have fun and do math, that'd be great, but that doesn't help you long-term. Okay, so back here, I pulled out the 1/2, and now I still have an e to the root x, I still have a 1 over root x, I still have an x dx, so that's everything that's still there. I can simplify this, right? X over root x could be simplified as just root x. And I'm going to put it out here in the front. Okay. So when we look at this new integral, remember the whole idea behind integration by parts was to transfer the derivative, to create a new integral that maybe would be easier than the original integral. And when you look at this and you compare this new integral to the original integral, you start to wonder whether or not you made things better or worse now, right? Because now we have a root x in front of the e to the root x. So we're kind of like wondering, are we going down the right road or not, right? Okay, so let's see, what now? I mean, this is where we are, so what now? Do you feel like we're kind of jammed up here? I mean, we could do another integration by parts, couldn't we? We could try another one. I'm not forcing your hand here. Does anyone have a suggestion? I mean, we can do integration by parts.
Use the context clues and say that we're probably going the wrong direction here.
Yeah, we kind of are. Let's try another integration by parts. So let's see if we can convince ourselves we're stuck. Okay, so we have two choices, don't we? We have the root x can be the u, or the e to the root x can be the u. Now, if we do the root x as the u, what's going to be the problem? If this is the root x, dv would have to be what? The e to the root x dx? What's problem with that?
We don't know the antiderivative.
That's right. The antiderivative of this is actually the original problem, isn't it? Isn't that the original problem? Yeah? So we're not going to be able to even complete the table. We can't even finish what the table is. So there's no way we can do that. Now we could have reversed it, but you have to be real careful, because if we reverse it and we do the e to the root x here, and we put the root x here, like that, what we're going to do is we're going to wind up undoing what we just did. Because notice, well, it's just going to get worse, is what I should say. Think about what would happen. Here we would have e to the root x times 1 over 2 root x. And then if we do the antiderivative here, we're going to have 2/3 x to the 3/2. I just did a power rule on that. And then I'm thinking about what this would be, and it's just getting nastier. I just keep on pushing more x's in there. Instead of the x's going away, it's just getting worse. Yeah? So I think I'm ready to give up on this approach. All right, so we're going to just start over. So the key to this problem is, like I said earlier, is to do something that you wouldn't naturally think would help. And that is, I'm going to make a basic substitution first. I'm going to let u be the square root of x. Now, that doesn't seem like that should get us anywhere, because when we were learning basic u substitution, the steps I gave you said, look for something and its derivative, right? I mean, that was the whole idea behind it. Look for something and then hope to see its derivative there also. Well, I see that. I see root x, but its derivative, 1 over 2 root x, is not there, right? Like I've already accounted for that root x. That's going to be my u. But the du is nowhere to be seen. Do y'all agree? Yeah? Okay. However, what is the square root of x? The square root of x is u. Yes? So couldn't I rewrite this as du equals 1 over 2u dx? Just replace the root x with u. And now what I'm going to do is just multiply both sides by 2u. And what I have is an expression for dx that involves nothing but u's. So that's tricky, huh? I mean, it works. It works. Let's see what the new integral would look like. We would have, let's see, the e to the u. That's me replacing the root x with u. And then the dx I'm replacing with 2u du. I'll go one step further. I'll pull a 2 out. I'll rewrite this as u e to the u du. Any questions? Okay. So there's where we are now. Anyone have any ideas on how we can go about that?
Yeah, I'll take integration by parts.
Integration by parts, good. So look, if I go back to the exam, where was it? You actually had this problem on the exam. This is number 9. The integral of x e to the x dx. We have u e to the u du. And actually, a lot of students got this problem right. A lot of students did okay on that one. So that's what we have to see here, is that we have to do an integration by parts now. So this is an example of a problem where what we did is we did a basic u substitution first, And then that got us to a point where we could do an integration by parts. Now, we have to be careful because I can't use U. I can't use ultraviolet minus voodoo because my original integral now, or this integral that I'm looking at, has U in it already. So I'm gonna have to use a variable other than U. So in my table, I'm gonna just pick a letter. I'm just gonna say W here in dV. So I'm gonna pick a W, and then the other part will be the dV, and then instead of ultraviolet minus voodoo, it's like, it's like that instead. Instead of U times V minus the integral of V times du, it's W times V minus the integral of V times dW. All right, so what should my W be? What do you all think? What would you rather pick?
U.
Yeah, the U or the e to the U? The U, right? Because when you take the derivative of that, you just get du, or 1, right? 1 du. And then the dv has to be the e to the u du, but that's okay because the antiderivative of that is just e to the u. So right here, when you're looking at that diagonal, which is normally voodoo, right? Now it's voodoo, I don't even know how to say that. VDW, right, is what you're going to have to integrate. It's just e to the u du, which you know the antiderivative of. All right, so here's where we are. We have 2, don't forget that 2 out front, times, now I'm ready to use the formulas, so I'm going to put in brackets. We do these 2 multiplied across the top, minus the integral of these 2, the diagonal multiplied, so e to the u du. And I'm running out of room. 2 times u e to the u minus the antiderivative e to the u, which is itself. And then I'm going to put a plus c, and I'm just going to throw it here on the outside. And that's it. I can distribute the 2 through, and there is one more thing I need to do. Distribute the 2, replace u with what it was. Remember, 2 was, u was root x. There it is. So, an unnatural U substitution first, which leads you then to integration by parts. Any questions? All right, the next problem that we're going to do, this one right here, sine to the n integral sine to the nth power of x dx. Now just remember, sine to the nth power of x really means sine to the x raised to the nth power. That's what that notation with the little n up there is, just taking whatever sine is and raising it to a power. Okay, so what is the antiderivative of this? So I'm going to, oh man, I didn't bring it up. You know what? Give me a moment. I'm going to go into WebAssign real quick. I'm going to bring up the ebook. Now, remember on our formulas, our formula sheets, I gave you, you have like 6 formula sheets you're allowed to use for the exam. Those come from the back of the book. But if you actually had the book with you and it was a new book and a previous student hadn't torn pages out, then you would actually see that there are, let me get back to, come on. So here are the pages that you have. Reference page 5, you have that on yours. You have reference page 6. This is a list of formulas for antiderivatives, and that's where your formula sheets stop, right? You don't have any more than that. That's not, you're not allowed to have anything other than this on the exam. What I'm referring to is these formulas that you're allowed to have on the exam. They stop here at reference page 6. The last formula you have here is formula 29. But if you looked at the book, there's another page, reference page 7. reference page 8, reference page 9. All these different formulas for antiderivatives. In fact, I've seen like textbooks that are just formulas for integrals. Like back before computers, they had these huge like databases of integral formulas, so that when an engineer got faced with an integral, instead of having to understand all the math behind it, they just went to the formula to make life easier. Because the engineer wants to solve the problem. They don't care about all the technique of integration to get to the answer. The engineer just needs the solution. So out of all these formulas, right, there's hundreds of formulas on these formulas. Well, actually, I guess it stops here. There are 120 formulas in the back of your book. I want us to I just picked one of them, and it is this formula number 73. I'm going to copy this. And what we're going to do is we're going to figure out where this formula came from. In other words, according to the formula sheet, if you want to find the antiderivative of sine to the nth power of u du, the answer to that is -1 over n sine to the n minus 1 of u times cosine of u plus n minus 1 over n times a new integral. And this new integral is sine to the n minus 2 of u du. So the way this formula works is as follows. Let me give you a specific example. Let's say we wanted to do sine to the 5th power of x dx. According to this formula, here n is what? For us, n would be 5, right? So let's just rewrite everything using that formula. Let's replace all the n's with 5s. So it'll be -1/5 sine to what power?
4th.
N minus 1, right? So sine to the 4th. Now I'm using x instead of u. X cosine x plus, okay, n minus 1 is 4 over n, which is 5, so 4/5 integral sine to what power?
3.
Sine to the 3rd, right? Sine to the 3rd of x dx. Okay, so what this formula has allowed me to do is take an integral of sine that was to the 5th power and then come up with an answer, but I still have an integral in here, but now I have to the 3rd power. So what do you think I'm gonna do next?
Keep on doing it.
I'm gonna use that formula again. So I'm gonna take this right here, just that, and I'm gonna apply the formula again to just that integral. And now I have a new n, right? My new n is 3. So let me go ahead and write this down. This is going to be equal to, I still have all this crap out front, 1/5 sine to the 4th cosine x plus 4/5. Now, here's where this new one's going to start. So I'm going to redo this now, this formula with n being 3 this time. So -1/3 sine to the 2nd x cosine x plus, now n is 3, so 2/3 integral sine to what power? What power?
Go
are we
to the
at?
first.
The first power. Okay, so it's just sine x, right?
First, yeah.
And there we go. Now, the good news here is that this new integral, I don't have to use the formula again, do I? Because I know the antiderivative of sine. The antiderivative of sine is negative cosine. You see that? So I could just rewrite everything. I'm not going to. Rewrite. And now this last integral is going to become negative cosine x, then plus a constant. Now, trust me, we still have all this crap in front of it, right? We still have to distribute numbers through and everything else. All I want you to see here is how the formula is used. You have sine to the 5th power. You're going to use the formula one time to get it down to sine to the 3rd, and then do it another time to get it down to sine to the 1st. Had that been sine to the 50th power, 50, you would have to do it one time to get it down to 48, and then another time to get it down to 46, and then another time. Does that make sense? Now, these are called recursion formulas because even though they're nasty, they allow you to chip away at these large powers of, well, in this case, large powers of sine. But if we go back and revisit the formulas, there's formulas for sine, cosine, tangent, cotangent, secant, cosecant. All of these have these things called reduction formulas. So again, I just picked one formula out of this thing. The point here is not, I don't want you to, I mean, I want you to know how the formula works. So there's how it works. I want you to see where the formula comes from, all right? Now this, I'm about to show you where it comes from. This would never be something I give you on a test as a problem. This would only appear on a test as a bonus, all right? Okay, but I think it's worth going through because it's important to understand that these formulas, you know, they didn't just fall out of the air, right? It's not like mathematicians stumbled upon some ancient scroll that had all these formulas that were given to us by some supreme being, right? I mean, like we had to come up with these things on our own. So where did this nice reduction formula come from? Well, here it is. You ready? Here's what we're going to do. The first step for this, and nothing I do here is going to seem like you would have come up with it. And I agree. Someone else spent a lot of time figuring out how to do this. But let's just appreciate what they did. So the first thing they did was they rewrote this as sine to the n minus 1 of x times sine of x dx. So think about it this way. Had we had that problem sine to the 5th x dx, the first step was to rewrite that as sine to the 4th x times sine x dx. So in other words, just peeling off one factor of the sine. So all it does is it takes the n power, takes it down to n minus 1, but now you have this new sign appear to the side. Got it? Now what that allows us to do is do integration by parts. And we can let the u here be the sine to the n minus 1 of x, and let the dv be that sine x dx that we peeled off to the side. I mean, the first step of peeling the sine off doesn't seem natural, but now that we've got this set up, y'all understand where I'm going to go with this on the table? I'm going to go with my u and my dv. I'm going to differentiate and integrate and see what happens. Okay, let's do the integration first because I think that's easier. The antiderivative of sine is negative cosine of x. And then this derivative here is a little bit tricky, so be careful. So remember, this is really sine of x to the n minus 1 power. So if you were to differentiate that, the first thing that happens is the n minus 1 comes out front, right? The power comes down. So I'm going to have an n minus 1 out front. Now sine is going to be raised to what power? What do we do to the power? Subtract 1, right? So when we take one more away from that, what we have n minus 2? Is that okay, everyone? Now, what do I still have next to that? I'm not done. All that was the power. All I did was brought the power out, subtracted 1 from the power. Still need to take derivative of what's inside. Right? So cosine x dx. All right, that's where we are, right? Let's go ahead and do ultraviolet minus voodoo now. So ultraviolet are these two multiplied together. So I'm going to write it this way. Negative sine to the n minus 1 of x times cosine x minus integral, leave myself a little bit of space. And now I have to do the voodoo part. So out of the voodoo, what constant can come out? Can we pull any constants out of the voodoo part?
Negative 1.
I can pull a negative 1 out. Are there any other things that are just numbers?
N minus 1.
N minus 1.
Minus 1. So watch the way I'm going to write this. I'm going to bring the negative out. It's going to change that minus to a plus. And then I'm also going to have an n minus 1 out here. Okay, what's left in there is still a sine to the n minus 2 of x cosine squared x dx. Everyone understand where I got the cosine squared from? I had two cosines, right? Okay, so let's just look at the formula. Let me go grab it real quick. Let's just see how close we are to this. All right, so in terms of our answer, some things look promising here. Sine to the n minus 1 of u is like this part. And then cosine, I've got cosine. See that n minus 1? I kind of have an n minus 1, don't I? Now here we have sine to the n minus 1 of u, and here sine, I'm sorry, sine to the n minus 2 of u. Here we have n minus 2 of x, but then we've got this cosine in here. This cosine squared is like not close to the formula, right? Like that's something that's not in the answer. So we're getting there, but we're not there, okay? We're getting there, but we're not there. All right, so what's the next step? This step is tricky. Right now, we don't know what to do with this, all right? We're kind of stuck here. Now, we could try integration by parts again. We could, but I'm gonna do something else. I'm gonna go back to pre-cal. I'm gonna remind everyone of the Pythagorean identity. We know that sine squared x plus cosine squared x equals 1. And you can solve this for cosine squared x by subtracting sine squared x on both sides, right? So cosine squared x is 1 minus sine squared x. So what I'm going to do is I'm going to replace this cosine squared x with that. And you know what? I'm running out of room here on this page. So I'm going to grab all this, go to the next page. So I'm going to, let's focus all of our attention right now on this integral. And we'll come back and we'll remember there's a bunch of stuff over here we still need to do. That integral is now sine to the n minus 2 of x times 1 minus sine squared x dx, just replacing cosine squared with 1 minus sine squared. Now distribute this through the parentheses. And when you do that, you get, let's see, sine to the n minus 2 of x minus what?
Would it just be sine x?
Close, not just sine x. You have to add the exponents, right? So you have to add n minus 2 plus 2. So the 2's
Oh, it
cancel.
would just be sine to the nth power.
Sine to the nth power. Sine to the nth power of x, all of that dx. Is that all right, everyone? Which you could also rewrite as sine to the n minus 2 of x dx minus the integral of sine to the n of x dx. So now I'm splitting it into two separate integrals. Okay, now why did I do this? Hopefully you see this. This is the original integral, isn't it? Isn't that the original integral? It's the original problem. So watch what I do now. I'm gonna rewrite, right now I'm about to rewrite all of this, but I'm gonna replace the part in red here with that answer. And I'm actually gonna write the original problem down also. So the original problem was the antiderivative of sine to the n of x dx. That's the original problem we started with. It's equal to negative sine to the n minus 1 of x times cosine x plus n minus 1 times, now here comes, I'm replacing now this right here, right? This whole integral in blue became this stuff right here. And that n minus 1 in front has to distribute to each of those, right? So I'm going to have integral sine to the n minus 2 of x dx, and then minus integral sine to the n of x dx. There. Any questions up to that point? Let me distribute. I have to take this n minus 1 and distribute it to that integral and to that integral. Right, it's got to go to both before I can remove the brackets. So my next line is going to be n minus 1 times the integral of sine to the n minus 2 of x dx minus n minus 1 times the integral sine to the nx dx. And I still have all this crap in front. Isn't this fun? Generating reduction formulas. Okay, there we go. There's where we are now. We're almost there. Because we recognize that this sine to the n of x dx is the original problem, I'm going to move it to the other side of the equation. And to do that, I'm going to basically reverse whatever I see happening. So right now we are subtracting n minus 1 of these. So if I want to move it to the other side, I have to add n minus 1 of them. So I'm going to add n minus 1 of these integrals. Just imagine that number n minus 1 was a number. You know, like what if that was like minus 3 times the integral? You would add 3, right, to both sides? Add 3 of the integrals. That's exactly what I'm doing here. And I have to do that on the same thing over here, add n minus 1 of those integrals to this side. They will go away over here. And how many of these now will I have if I add these two together? So I have one of them, right? There's one of them here, one of those integrals, and I'm adding n minus 1 of them. So what's 1 plus n minus 1?
N.
Just n. So I have n of these integrals equals negative sine to the n minus 1 of x cosine x plus n minus 1 of these integrals of sine to the n minus 2 of x dx. One more step. Who sees the last step?
The divide by n.
Divide by n. That's it. Divide this side by n, which makes that n go away. When I divide this by n and this by n, really that n can just be like underneath that n out there, and then this n, well, let's just look at the formula again. Because we're there, okay? We're there. If I can go back and find this formula. So our first term here matches this one exactly now, right? Negative 1 over n. So just imagine that that's a negative 1 over that n out front, sine to the n minus 1 cosine, or sine to the n minus 1 of x cosine of x, and then plus n minus 1 over n, that's this, and then the integral with the power taken down 2. And that's our reduction formula. That's where it comes from. So it's pretty remarkable when you look at these integral tables at the end of books. Every single one of them comes from some sort of usage of integration by parts or some technique that we have, and that's where the formulas are generated. Okay, we are going to say that we're officially done with integration by parts. Not that it's done like you'll never see it again, but we're done covering the problems involving integration by parts. We're ready to move on to the next section, which is chapter 6, section 2. Are y'all ready? Yeah? Okay. So 6.2. Let me tell you a little bit about 6.2. 6.2 is really going to take us 2 days minimum to get through this, maybe 3. Okay, so today we're going to start it. All next class will be on it, and we'll probably have a little bit that carries over into next week. All right. So the way that this section works is there's 2 parts to it. The first part of it is called trigonometric integrals. Okay, trigonometric integrals. And then what we have after that are what are called trigonometric substitutions. Okay, so they're 2 different things. trig integrals, trig substitution. When we do trig integrals, we actually have to understand that, and we have to be good with it, like proficient with it, in order to do the second part of this section. Like you cannot do the trigonometric substitution without knowing the trig integrals. In fact, when we do a trigonometric substitution problem, our goal is going to be to turn it into a trig integral, which is what the first part of the section is. So the first part of the section is vital to us. Good news is that it's easier than the second part of the section. So we should at least hopefully feel comfortable with this, at least in the beginning. So the first part of this is stuff that we should already know. Everyone knows the antiderivative of sine. Everyone knows the antiderivative of cosine. I also talked to you all about what happens if you have some number in front, like a linear expression inside of a sine or a cosine function, that you have to scale it out. Remember I said, you know, like if you have the antiderivative of cosine of 4x dx, that this will be 1/4 sine 4x plus c, that you have to account for that 4 by scaling it out, right? Do you remember us talking about that? Okay, so that's stuff that we already know. All right, so now we get into trig integrals, and I have a separate page for us to look at. Okay, so trig integrals, trigonometric integrals. Our goal here is to be able to evaluate integrals that involve the 6 basic trig functions. So any integrals that either have sine, cosine, tangent, secant, cosecant, or cotangent in them. Now, that's all that can appear in them. So it's only some combination of the 6 trig functions. You can't have, so like this would be okay. An integral that looked like this would be a trig integral, because it has sines and cosines in it, right? Raised to different powers. So that's a trig integral. Let me show you something that's not a trig integral. That's not a trig integral because it has an x here. And x by itself is not a trig function. So we're only wanting to deal with function or integrals that involve just the 6 basic trig functions, not mixed with anything else. All right, and you could even change that. Let's make it over x. That's not a trig integral. Okay, just trig functions. So the good news, I guess, if there's good news, is that we do have a strategy for this. We have kind of a method that you'll follow, and the method that you follow is in your formula sheets. This is a separate formula sheet in Canvas that you can print out, and it tells you how to go and attack trig integrals, and it gives you these 2 scenarios: how to integrate when we have sine and cosine, and then another set of steps on how to integrate when we have tangent and secant. These are 2 different procedures. So you have that. I'm giving that to you on a test, right? You can use this. And then the second part of this has to do with the trigonometric substitutions, which we're not talking about today. So just be aware that you will have access to these notes and steps when you get to the test. But the good, I guess, the thing you're going to have to remember is that there are some identities from pre-cal that we're going to be using to do trig integrals. And there's 2 groups. The first group is the Pythagorean identities. And those are identities that everyone here should be familiar with. Of course, the first one, sine squared theta plus cosine squared theta equals 1. That identity, I hope, is like burned into your brain, right? And then there's actually 2 other Pythagorean identities that are related to this one. So those 2, and again, these are on your formula sheets. And then we have these other formulas from pre-cal called the half-angle formulas, or the power-reducing formulas. I like to call them power-reducing formulas because what they essentially do is they allow you to take the power off of a trig function. So like here we have like sine squared. You can get rid of a sine squared and make it so it no longer has a power of 2 if you convert it into this new formula. The catch to it, though, is that the power, okay, the sine switches to a cosine, that's one thing. But then also, instead of having a power of 2, you double the angle. The angle that's inside the trig function now doubles. And that's, I've heard this formula called the half-angle formula. I've heard it called a double-angle formula. I've heard it called power-reducing formula. It's called all different things. But I'm going to refer to it as the power reducing, all right? And so these two formulas for cosine squared and sine squared, both of those formulas you should be familiar with. Now, the way I'm going to write them, notice that this fraction here could be rewritten as 1/2 times 1 minus cosine 2x. And this one could be written as 1/2 1 plus cosine 2x. Those are the ways that those are the ways that I'm going to write them. Okay, I'm going to pull the 2 out in front. I'm going to put it as a half. And the reason I'm going to do that is because remember that half, if it's in an integral, the half can just come out. So we may as well just work with it, not even in the integral. All right, you ready to go get at this? All right, so the best way to do these is just to do some examples. Okay, so that's what I'm going to do. I'm going to bring up our first example. And then we are going to refer back to the steps. So we're going to do sine cubed of 4t. I'm going to start a new page here. What is the antiderivative of sine cubed of 4t? I'm using t instead of x. Somebody is going to ask me, or you might be wondering, can we just use that reduction formula we just did, right? Didn't I just show you a reduction formula on how to deal with sine to the n? The answer is yes, you could, but on a test you don't have the reduction formula, right? You don't have that formula on the test, which means that I would expect that you do this using the trig integral, or doing it as a trig integral, not using a formula. So let's look at the steps, all right? And what do you think? You want me to do the steps? I'll do it off the formula sheet. I'm gonna just grab it right off the formula sheet, just like this. I'm gonna copy this whole thing, because this is what you're gonna have on the test. So it's probably useful if we just use that. Use that here now. I'm just gonna throw it here so you can see it. Whoa, it's huge. All right, so here we go. We have a trig integral, right? It's an integral. It involves a trig function, one of our basic trig functions. So we are thinking trig integral. We're also, we can't do this with a basic U sub. Okay, integration by parts doesn't look very promising, although it could be done with integration by parts. We're thinking trig integral, trig integral. So how do we integrate? How do we integrate powers of sine and cosine? Well, the first thing we have to do is ask ourselves this question. If the power of cosine is odd, okay, so we don't even have a cosine, do we? Right? So we don't even have a cosine. All right, the next question. If the power of sine is odd, yes, that's us, right? We have an odd power of sine. Okay, what we're gonna do, and this is weird language, this is the way that the author of the book says it, we're going to save one factor of sine. Save one factor of sine, what the hell does that mean? It means factor out one factor of sine. So I'm going to rewrite this as sine squared 4t times sine 4t dt. So I have saved one factor of sine. The one that I've saved is this one. Okay, I have saved that on the side. I've pushed it out to the side. Everyone good? Now look at the next step. Use the Pythagorean identity, sine squared x equals 1 minus cosine squared x, to express the remaining factors in terms of cosine. Okay, so what's happening here? We started with an odd power of sine, right? Odd, that's what we're using this step. This is what we do when we see odd powers. We pull one sign off to the side. So what can you guarantee me about that power right there on the new expression? What can you guarantee me about that power? It has to be what?
Squared? Or
Sorry?
it has to be squared?
Squared, in this case it is, because we started with sine to the third. What if we had started with sine to the fifth?
It has to be even?
It has to be even. Okay, does everyone understand that if we start with an odd power of sine and we peel one sign off, then whatever's left has to be even? Yes? Now, this relationship that we have, sine squared x plus cosine squared x equals 1, that Pythagorean identity is a relationship between sine and cosine when you have sine squared or cosine squared. Let me ask you, does this formula extend to evens? Like, can you just change that to the fourth and it's still equal to 1? And then could you extend this to the sixth? Are those two true? I mean, it works for 2. Does it work for 4 and 6 and 8 and 10? What do you think? I'm seeing no, shaking heads of no, and that is correct. It is no go here. No go, all right? Unfortunately, it does not, all right? But let's follow what it says. We're supposed to somehow use this. Okay, so let's just use it. I can rewrite that sine squared 4t using that as what? If we use this, solve it for sine squared, we get 1 minus cosine squared x, right? So how could we rewrite the sine squared of 4t? Anyone?
1 minus cosine squared of 4t.
Yep, 1 minus cosine squared of 4t. So I'm going to rewrite this as integral, parentheses, 1 minus cosine squared. Now we still have to have the 4t in there. That's the argument. Sine 4t dt. Now, why in the world would we take sine squared of 4t and rewrite it in terms of cosine? Like, why switch it to cosine? This expression just got more complicated, right? Instead of 1 term, now we have 2 terms. Why? Why do this?
What if we take like a U sub and we change like either sine or cosine into the other one?
Exactly. That's exactly precisely why we're doing this. Look, we started out with an odd power of sine, right? We peeled one off, and that left us with this thing that we were saving, right? We are trying to program this problem. We're trying to program it for this to be our du on a basic U sub. We're trying to make that the du, and that means that our u needs to somehow have cosine in it, right? So let's take this over here, and because it's an even power of sine, I can use the Pythagorean identity to switch it to cosines, and now I can make a basic U sub. Now, what you choose for your u is not up to you in this case. It has to be the cosine, because the derivative of that needs to be sitting off to the side, which is the sine part. So that's what this last step is here. Let me see, what color have I not used? This isn't going to show up. So let me see this last step here. Can you all see that step right there? Substitute u is equal to cosine x. That's the last step of the procedure. All right, so I'm going to do that. I'm going to move all this down. Okay, so I've rewritten it, and now here comes my basic U substitution. U is going to be equal to cosine of 4t, and that's it, just cosine of 4t. That's it. The derivative of this is -4 sine 4t dt. So the -4 comes from the chain rule, right? Derivative of sine is negative, derivative of cosine is negative sine. So we have the negative comes from the derivative of cosine, and the 4 comes from the chain rule. Now we almost have that, right? Sine 4t dt, sine 4t dt. So I'm going to have to scale both sides, right? Get rid of that -4. And I think at this point, we're ready to rewrite the integral. My u is going to be cosine 4t. My sine 4t dt is going to be 1/4 du. So let's go, new integral. Any volunteers to tell me what the new integral is going to be?
1 minus u squared times du.
Okay, so integral 1 minus u squared. That's just replacing that cosine 4t there. That's replacing that with u, but not forgetting that it's squared. And then the blue part, the sine 4t dt, gets replaced with negative 1/4 du, right? I'm going to pop that negative 1/4 out here and put the du here. That make sense? And that you should be able to handle, right? That's just a basic, that's just a basic integral, just power rule. Right, just doing one at a time. So the negative 1/4 will be sitting here. Let's go ahead and take the antiderivative of each one. Antiderivative of 1 is just going to be u. Minus antiderivative of u squared is 1/3 u cubed. And then we'll have a constant. And then we just replace u with what it was. And u was cosine 4t. So negative 1/4 cosine, not to the fourth, cosine of 4t plus 1/12 cosine cubed 4t plus c. There it is. I distributed, right? The negative 1/4 got distributed. And then I went ahead and cubed the cosine, and the other one I just left it alone. What do you think? That's how you deal with sine to an odd power. You peel off a sine and you use a Pythagorean identity. Any questions? Okay, I'm going to do another one. I'm going to make this one up. Moving on, moving on, moving on. Okay, how about this? Sine to the 7th beta t dt. Beta is a constant. We don't know what it is, but it's just a number. The variable here is t. You know that because it's dt, right? You have a trig integral. Sine to an odd power. First thing we do, peel off one factor of sine. Nope, 6th power. Now this is where things get a little tricky here, because that's not sine squared, right? So I cannot replace that with 1 minus cosine to the 6th, right? I can't do that. So does anyone have any ideas on how we can still use the Pythagorean identity?
Could we rewrite the sine to the 6th as sine squared beta t, and then in parentheses to the 4th power?
To the 3rd power. Because you would be multiplying those powers. So 2 times 3 would give you the 6. That's exactly right. We're gonna use the fact that sine to the 6th is really sine squared, all of that cubed. Good. Okay, now I can turn that sine squared beta t into 1 minus cosine squared beta t, but all of that still has to be cubed. All of it. So the whole point of all of this, peeling off the sine and rewriting everything in terms of cosine, is so that now you can make a substitution. Basic substitution, u is what?
Cosine beta t.
Cosine beta t. And the derivative of that will be negative 1, not negative 1 over beta, negative beta sine of beta t dt. So again, derivative cosine is negative sine, but then you have to pop that beta has to come out. And I'm going to scale both sides by 1 over beta to get rid of it. And at this point, we're ready to rewrite it. We have sine beta t dt is right here. We know that cosine beta t is going to be replaced with u. So let's see, let me call on someone. It's been a while. It's been a while. How about Coleman?
All right. So you're just wanting the rewrite?
Yeah, just what is the whole integral in terms of u?
Okay, it'll be negative 1 over beta.
So you pulled the constant out at the very beginning, good.
And then it'll be 1 minus u squared
U squared,
to the third, all of that.
that to the third,
And then times du.
du, there it is, that's it, okay? So what we've done is we've converted a trig integral with a basic U substitution. We turned it into, in this case, a polynomial, right? This is just a polynomial. Coleman, do you have any idea how I mean, like the previous problem was nice, right? Because when we got to that last step, it's just 1 minus u squared. We just did them individually and we were happy. Can't do that here, can we? Because that cube. So any idea of how you might go about it?
Can we do another substitution?
Maybe a substitution might work. But how about just do some algebra? Like what's 1 minus u squared cubed? Like what is that? Like what is 1 minus u squared times 1 minus u squared times 1 minus u squared, right? Now, I mean, that you wouldn't want to do that if that power was like to the 7th or something, but cubed, it could be done, right? You can multiply that out. And then once you did that, you would have just a bunch of powers of u, right? And you just find the antiderivative of each one. So I'm going to put here dot, dot, dot. And this might start happening more often now, okay? We get the integral to a point at which we say, okay, we can handle that from here. Because of time, we just won't have time to actually go all the way to the answer in class. We're just going to be like, okay, that we can do. And a day and a half from now, we're going to do these trigonometric substitutions. And when we do those problems, we're actually going to be like getting it to here and being like dot, dot, dot. Like, okay, so now we know, you know what I'm saying? Like it's all going to build on itself. All right, does this seem okay so far? Sine to an odd power, we're in business. Okay, let's see what the next example is that I have here for us. Gonna make one up. How about cosine? Let's just go cosine to the 5th. So without bringing up the little the little cheat sheet thing, formulas, what do you think the approach is going to be on this? Can we use the same tactic? Okay, you want to peel off a cosine? Okay, if we peel off a cosine, so right now we have cosine to an odd power. We've been dealing with sine to an odd. But if we have cosine to an odd, if we peel off 1 power of the cosine, now this piece, cosine x dx, is going to be our du part. So we're thinking that we want that to be the derivative, right? So that means we have to get the cosine to the 4th and switch it, right? Switch it to sines. So we're going to use the same idea, the same principle. We're going to have to rewrite this as cosine squared x squared cosine x dx. And let's see, is Jane around? Jane?
Yes.
Jane, are you following what I'm saying here? Like, Using the same method from last time?
Yes.
Okay, so we peel off the cosine. Now we've got a cosine to an even power. We're guaranteed it's going to be even. And then we rewrite 4 as squared squared. And then what can I rewrite the cosine squared as?
Minus sine.
Wouldn't it be just the sin?
We're using the Pythagorean identity, right? We're using this identity. We want to rewrite cosine squared. So solve for cosine squared by moving the sine squared to the other side, right? Which would become,
Wouldn't it be the 1 minus, no,
yeah, 1 minus sine squared. There you
Right,
go,
right, yeah.
just like that, okay? Everyone see that? This becomes this. Now the whole point of that, right? The whole point of that, Jane, is so that we can now make a basic U substitution. What will your U substitution be, Jane?
wouldn't it be sin 1 minus sin squared? Or,
You don't need the square, just take the sine. Just take the sine because the derivative of sine will be the cosine, right? That's what you want, and you have that cosine sitting there. So this is just a basic substitution of U is sine x. Du would be our cosine x dx, which we have. There it is. Cosine x dx is sitting there just waiting for us to use it, right? Okay, how about Maribel? Is Maribel here?
Yeah, I'm here.
Oh, there you are. Hey. Okay. So Maribel, are you following this okay?
Yeah, kind of, I guess.
Yes, it's okay?
Yeah, I guess.
Sounds like you're being agreeable.
Yeah.
Yeah, okay. Well, then do you have any questions about what I've done so far?
No.
Do you know how this integral will be rewritten?
Would it be
We're replacing sine with u,
U?
right?
Mm-hmm.
We're replacing cosine x dx with du.
It would be 1 minus u and then
1 minus u
2 squared.
squared. Yeah, don't forget that green squared there, right? 1 minus u squared, but then all of that is still
On
squared, right?
to the second power.
And then cosine x dx is just your du. Now this one, I'll actually expand that because 1 minus u squared times 1 minus u squared, I could do that on the side. That's what you would get if you took 1 minus u squared and multiplied it times itself. Right, FOIL, like that. And then du. I'm gonna go fast now. U minus 2/3 u cubed plus 1/5 u to the 5th plus a constant. Now I'm just doing power rule on each one, and then I replace u with what it was, which was sine. There it is. The antiderivative of cosine to the 5th x is sine x minus 2/3 sine cubed x plus 1/5 sine to the 5th x plus c. If we take the derivative of that, we should get back the original integrand. I'm not doing it, but we should get it back. Okay. So far, it appears that we can handle sine to an odd power and cosine to an odd power. We just peel off one, then we use the Pythagorean identity, do a substitution, and just crank it out. We'll have a polynomial at the end. We just do, individually power rule on each one. All right. So does it get dramatically different when we have an even power? Let's take a look. So let's say we have sine, and let's start easy. Let's go sine squared x dx. Okay. So we have an even power, right? If we look at the steps, did I delete the steps? I think I did. Oh, well. Okay, so, sorry, I'm gonna have to grab this again. It's gonna come in all big. I can't figure out how to make this not come in all big like this. All right, so we have sine squared. So first thing it asks, if the power of cosine is odd. Okay, well, we don't have that, but we've done that, haven't we? We've done that before, but not this, that's not this problem. If the power of sine is odd, we don't have that now, right? Okay, if the powers of both sine and cosine are even. So this next method, or this next way to do it, is whether or not we have cosine or sine to an even power, all right? You're gonna do the same thing on both. So what it says is just use the half angle identities. Use the power reducing formulas, depending on whether or not it is you see sine or cosine. So for us, we're gonna be using this one, okay? That's the one we're gonna use. So we're just gonna rewrite it. So let's do that. This just gets rewritten as 1/2 1 minus cosine 2x dx. I can pull the 1/2 out. And now I have great news. You can just integrate those individually. Just take the antiderivative of each one. So 1/2, the antiderivative of 1 is x. And then the antiderivative of cosine of 2x, drum roll for Alexis. Is Alexis here?
I'm right here, sir.
There you are, okay.
I'm sorry, hold on. I was still writing it down.
Okay. You have Alex on your thing, but you want me to change it or you want to keep it?
It really doesn't matter.
Okay. All right, so antiderivative of cosine 2x.
Antiderivative, will it just be sine 2?
Sine 2x? Missing anything there or no?
Oh, no, I feel like I am.
What about that 2? You got to take care of that 2.
Oh, wouldn't it just be the 2 without the x?
No. The antiderivative of cosine 2x.
Oh, I mean x squared, right?
No. We're doing antiderivative. So this is what we started this section with. I don't know what page it was. No. Oh, yeah, I'm looking at the wrong thing. Here we go. So when we started this whole thing out, we said, remember, we know the antiderivative of sine and cosine. We also know the antiderivative of sine and cosine when there's a number in front. Antiderivative of cosine of a times x is 1 over a times sine of ax. So we have to scale it, right? You can't forget that. We have to scale that.
Oh, so the 1/2, yeah.
1/2, there we go. 1/2 sine 2x, and then plus c. And that's it. We could distribute the half through.
Okay.
And we're done. So with that even power on sine, that wasn't too bad, was it? Would you all agree?
Yeah, wasn't too bad.
Not too bad. Okay. Well, unfortunately, it's going to get bad. All right, because that was sine squared. Sine squared is the easy one. Let's take something worse, like sine to the 4th, maybe. And this is where the wheels start to come off a little bit. So sine to the 4th x dx. All right, Alex, you're off the hook. All right, so we have an even power, right? We have an even power. So because we have an even power, if we're following the steps, the steps just say, hey, just use one of these, you know, and you're in business. Have a good day. That's all it says. But as we're about to see, there's a lot more work involved now, because the best I can do is rewrite this as sine squared x squared. That's kind of what Christian said earlier when we had the sine to the 6th. We did sine squared cubed. Well, the best we can do here is sine squared, then squared. Now we can rewrite the sine squared on the inside as 1/2 parentheses 1 minus cosine 2x. But then all of that still has to be squared dx. So I hope that you see that the sine squared x, I use the power reducing formula to turn it into the 1/2 times in parentheses 1 minus cosine 2x. So that part okay?
Yeah.
But you can't just take the antiderivative of those, because the whole thing is being squared, which means you have to square it. So I'm now going to square things. Now watch what I'm going to do. Because I have multiplication right here, I have multiplication right there, I'm going to square the half, and I'm also going to square everything in parentheses there. So it's going to look like this. I have a half squared. A half times a half is a fourth. I'm going to pull it out of the integral. There's my fourth. Then I still have to square this part. I haven't done it, but I'm just algebraically, I've taken the 1/2 and I've squared it and I've pulled it out. And I've left the 1 minus cosine 2x in parentheses squared. And then I'm just going to step to the side here and square it. And that means I have to FOIL it. So 1 minus cosine 2x, and then the inner one is minus cosine 2x, that's minus 2 cosine 2x. And my last term, this one you have to be careful with, is positive cosine squared 2x. Right, because we had to multiply cosine 2x times cosine 2x, that's cosine squared 2x. So this now becomes 1/4 integral 1 minus 2 cosine 2x plus cosine squared 2x dx. Are there any questions on where I got any of that?
No.
We're good? Okay, let me see here. How about Christopher Ver? You're up. I just have some questions for you.
Yes, sir.
Okay, so when you look at this, we have 3 separate things, right? 1, 2, 3.
Yep.
Okay, how about the first one? Are you okay? Can we take the antiderivative of the first one?
Yes.
Okay, so let's go ahead and start doing this. We're going to have 1/4. Okay, antiderivative of this. What's the antiderivative of 1, Christopher?
X.
X, okay. Minus 2 is going to come for the right. How about this next one? The cosine 2x. We know the antiderivative of that? You're on mute, Christopher.
It would be 1/2 sine 2x.
Yep, 1/2 sine 2x. So things are running pretty smoothly so far, aren't they?
Yep.
I mean, we're doing okay. And then Christopher hits this one. And
Oh.
Christopher looks at that and goes, shit, right?
Mm-hmm.
Because it's cosine squared 2x. So Christopher says to himself, all right, look, I've got the first 2, but I still have to figure out what this integral is. That makes sense? So it's like we took the 1/4. The 1/4 is going to go through here and here. So we got this all taken care of. But we still had to take care of this one, and we couldn't forget the 1/4 in front. Does that make sense? Okay, so Christopher, any idea of how we're going to go about this? We have cosine squared. Is it a trig integral?
Yeah.
Yes. What's the power that you see on that trig function? Even or odd?
Even.
Even, okay. And what do we do when we see even powers?
Use a half angle.
Yeah, use a half angle. So we're gonna have to use a half angle again, aren't we? Right? We're gonna have to use a half angle again. But it's like its own problem now. Now, I've already distributed the 1/4 through here, just so everyone knows that's where these two pieces came from. But we're here with Christopher, and Christopher is suggesting half angle formula. Good job, Christopher. Let's move on to Stephanie. Stephanie? I see Stephanie. Let's see if Stephanie's there. Stephanie, are you there? You're muted. No, Stephanie?
Yeah.
Oh, there you are. Are you with us or no?
Yeah, it's because my thing breaks up a lot, so I hear you in parts sometimes.
Okay, are you with us? I'm going to ask you for what this turns into. Are you okay with it, or?
I'm a little confused on it since we just started on it like today, like the lesson. I'm confused.
Okay, that's fine. That's fine. I mean, I just want a response, so that's all I'm looking for. How about you, Seth?
Would it be 1/2 1 minus sine 2x?
Cosine. Hold on. Where are you getting it? So we're using the power reducing for cosine. Let's go back and look at it. Let's just, so we have it here. The power reducing for cosine. Cosine squared of something, right? Cosine squared of something is 1/2 times 1 plus cosine of 2 times that something, right? That's important. Whatever we have here in the new expression, it's doubling it, right? It's doubling it. So here I'm going to have plus, right? Not minus. And
Cosine
then
of
cosine of what?
4x?
4x. 4x. We have to double the 2x. A lot of students miss that part. They put 2x again, but it's actually doubling it. And then dx. I'm just going to work this side down. This is going to be 1/8 integral 1 plus cosine 4x. We're almost there. Dx. This stuff still comes down. And now, Yusuf, you know the antiderivatives of those?
Yes, sir.
Okay, go ahead.
Is going to be just x.
X.
And then the second one's going to be 1/4 plus
Mhm.
1/4 negative sine of
Just sine,
sine of 4x.
right? Okay, there you go. Let's see. So 1/4 x minus 1/4 sine 2x plus 1/8 of all that stuff. I'm going to go, because we're almost out of time, but I have enough time to finish this. This is so I distributed the 1/8 through. And there is one more thing I can do. I can put these two together because they're like terms. So when I put those two together, that becomes 3/8 x minus 1/4 sine 2x plus 1/32 sine 4x plus c. There it is. All right. A little bit tricky on that problem. All right, so what's for homework? You should definitely make sure that you're done with the integration by parts homework, 6.1. Make sure that that's done. As far as 6.2 is concerned, we're still very, very limited on what problems we can do. So I would say to get started on 6.2, you should probably only look at like the first, I don't know, I would say the first 6 problems for sure are fair game. If you want, you can try and go out as far as 16. So 1 through 6, anything 1 through 6 you should be okay with. Anything from 7 to 16, you might be kind of stepping to the edge of the cliff on that one, on those. All right. We will do more examples where you'll be able to do those, but just I haven't shown you enough yet. I would recommend that if you do the homework, you bring this formula sheet up and you just follow it. You know, do you see an odd power of cosine? Then do this. You see an odd power of sine? Do that. If you see even powers, then do this. All right. All right. We will come back and do more. Any questions?
Oh, are you gonna send us the email?
Yeah, I'll send it right now.
Okay.
Solutions to the exam, right?
Yes, sir.
You know what? Right now in the chat, I'm going to send it in the chat, just so people don't even have to go check their email. I think this is it. Yeah, I think that's it. I'm gonna download that and open it. Let me see. Because I accidentally sent one the other day that was only the first page. Oh, that looks like the whole thing. Okay. Did y'all get it through there? Did it come? Yeah. I'll still send it in Canvas just in case. All right, everyone. Have a good day. I'll see you on Wednesday. I'll be in the office hours here in 20 minutes if anyone wants to talk.
Oh,
See you